Hi girls. Okay, so today we're going to be learning about using inverse functions, and we are on page 190 and we're talking about lesson 3.4. So in this section we're going to be looking at the part right before example number 1, talking about the inverse relation. And basically on your chart there it shows that an inverse relation flips your x values to your y values and then your y values to your x values. So let's go ahead and look at that chart. It gives you your x values, the blue one, gives you the x's at 0, 1, 2, 3, and 4. And then your y values at 6, 4, 2, 0, and negative 2. After that, it says that the inverse function of this, or the inverse relation, will flip them. So now your y values will be the x values of the previous problem. So we're looking at problems right up over here. So your y values will now be 0, 1, 2, 3, and 4. And then those x values will be the y values from the problem, so 6, 4, 2, 0, and negative 2. So essentially we're just flipping them. Your x becomes a y and then the y becomes the x. So in example number 1, we're going to go ahead and move on. We have the equation y is equal to 3x minus 5. And in this example it's asking you to find the equation for its inverse. So what you need to do is you are flipping your x and your y values. So we're going to take our y and our x and flip them. So we're going to have x is equal to 3y minus 5. So we switch places. After you do that, you are going to solve for your y now. So we're still solving for y. We want it to be in that slope-intercept form. So we are adding 5 to both sides. And you get x plus 5 is equal to 3y. After you do that, your last step is dividing both sides by 3. So your final answer will be y is equal to x over 3 plus 5 over 3. And that is your answer. Now if you wanted to leave it in if you wanted to leave it as y is equal to x plus 5 over 3 altogether, that's fine too. Both of these answers are totally acceptable. And that would just be your inverse function. Okay? Alright, let's go ahead and move on here. So in this next example, we're trying to verify that f of x equals 3x minus 5, and f negative 1, or f inverse of x, is equal to 1/3 x plus 5/3. Right before example number 2, it gives you this key concept box, and I'm not really a fan of how it explains the f inverse, so I want to explain it differently. It gives you that f negative 1 is read as f inverse, or the inverse of f. Okay, so this is what we're going to be qualifying or labeling our inverse as. So it's going to look just like this, f negative 1, but it's read as the inverse of f or f inverse. So if you're trying to verify something as being an inverse function, and we're moving on to example number 2 over here, we're trying to prove that this function f of x, 3x minus 5, has an inverse function of f inverse of x is equal to 1 over 3x plus 5 over 3. So if we're trying to verify this, then all we need to do is use this original equation and find the inverse of it. And when we find the inverse of it, we need to make sure that it equals this over here. So in finding the inverse, remember f of x equals y. So we're just going to go ahead and plug in y here. So we get y is equal to 3x minus 5, and we are going to solve for our y. So after we solve for our y, we need to before we solve for our y, we need to switch these. And then we can solve for our y. So in solving for our y, again, just remember, is exactly the same as example number 1. So we're adding these 5s to both sides, and then we get x plus 5 is equal to 3y. And then our last step, we divide each side by 3, so we get x over 3 plus 5 over 3 is equal to y. And in order to make this look exactly like our inverse function up here, we're just going to make it 1/3 x plus 5y. We're pulling that 1/3 out. And those are the same. This equation here that we just found out is identical to the one that we were trying to verify. So that's how you would verify it. You would just go ahead and interchange or switch out your x and your y right over here, and then solve for your y value. So when verifying that a function and an inverse are the same, you would just go ahead and find the inverse of that original function, and then from there solve for y. So next we're going to go ahead and move on over to example number 4. We're skipping over example number 3. But before we do that, we're going to look at the next page on 192, the inverses of nonlinear functions. And it's basically wanting to ask you, or for you to tell, whether or not that the inverse of a certain function will be considered a function or not. So you can actually figure that out before even figuring out your inverse. So let's look at the left-hand graph there. It gives you this graph just like this, and it gives you a parabola facing up, which we learned about in our last chapter. And you can tell whether or not the inverse of this function will be considered a function by doing a horizontal line test. So if you're to draw a horizontal line through this graph, I want you to see how it intersects at 2 different points. And if it intersects at 2 different points on this graph, then you know that your inverse function will not be considered a function. Now, the vertical line test tells you whether or not the function that you have itself right now is a function. So if we draw a vertical line like this, notice how it only passes through 1 point. That means this parabola will be considered a function. However, doing the horizontal line test will tell you whether or not this graph's inverse will be considered a function. So it turns out that once we take the inverse of this parabola, we're going to get something like this, which is like a sideways parabola. And notice if we do the vertical line test on this guy, it crosses through 2 points. So in fact, this will not be considered a function. However, we already knew that based on its parent graph or its original graph. So now let's go ahead and move on to example number 4. Example number 4 talks about this function right here. We have f of x is equal to x squared. And it wants it for all values of x greater than or equal to 0. So in this case, if we were to draw this graph, it would be only half of a parabola because the domain is restricted to all values of x that are positive or 0. And then it wants you to graph its inverse. So first off, we need to find its inverse. And finding its inverse, we're going to make this f of x equal to y. And then we could switch out both our x and our y. So our y becomes an x and our x becomes a y. And then from there we solve. So we're going to take the square root of both sides, and in doing so, remember we get our plus or minus. X, square root of x is equal to y. So this is going to be our inverse function right here. So we have inverse function of x will be equal to plus or minus square root of x. Now remember, we wanted it for all values of x that are positive, so we can go ahead and erase this negative, the plus or minus sign, and just keep it with a positive x. And knowing that, the graph of this function will look just like this. And you can tell that by either plugging in random points or putting it into a graphing calculator. It's up to you. Example number 5 talks about finding the inverse function of a cubic function. So it's the same thing here. We're still interchanging out our x and y's and then solving for the y. So it gives you the function f of x is equal to 2x cubed plus 1. And we're finding the inverse of this function right now. And before we do that, it's asking you to determine whether or not the inverse of the function will be considered a function. So in looking at this graph right here, if you graph it on a graphing calculator or plug it in to your phone somehow online, you're going to get this kind of graph right here. And remember, we use the horizontal line test in order to determine whether or not this inverse of this function will be considered a function. So again, if I draw a bunch of horizontal lines, notice that every single line that I draw that's horizontal, it's only intersecting at one point on this graph. So in fact, this graph's inverse will be considered a function, which is good. So find the inverse now. We're going to go ahead and make this f of x equal to y. So you get y is equal to 2x cubed plus 1. Then you can go ahead and change out your x and y. So x is equal to 2y cubed plus 1. Getting the y by itself, we subtract 1 on both sides. X minus 1 is equal to 2y cubed. Divide both sides by 2. You get x minus 1 over 2 is equal to y cubed. Now finally, last step, we need to take the cube root of both sides. So we have cube root of x minus 1 over 2 is equal to y. And this will be our inverse function of the function f of x is equal to 2x cubed plus 1. So the reason why I didn't have to have a plus or minus on this equation is because of this cubed root here. And if you recall from section 1, it talks about cube roots and how there's only one solution for cube roots because that nth root is going to be an odd. Now these past couple of examples have been examples of finding inverses of relations and functions. However, in these next few examples, we're going to be finding the inverses of models. So finding the inverses of models is a little bit different. So if you flip back to example number 3 on page 191, we're going to try and find the inverse of a model here. And in this word problem, it gives you this equation, r is equal to 3 over 8 L minus 5. And the first part of it asks you to find the inverse of this model. So in finding the inverse of the model, you don't actually need to switch out your r and your L. All you're doing is putting it in different terms. So think about it in terms of like x and y. In this part here, in this original equation, this is all in terms of L. So finding the inverse of a model, you're going to be putting it in terms of r. So what you need to do is just get L by itself. So you're not interchanging anything, you're just getting the L by itself. So you start off with adding 5 on both sides, and you get r plus 5 is equal to 3 over 8 L. And then your last step there, you can multiply both sides by the reciprocal, so 8 over 3. And then you get 8 over 3r plus 40 over 3 is equal to L. So now you've taken the inverse of this model, and now everything's in terms of r. That last part there wants you to find the length at which the band provides 19 pounds of resistance. So if you're doing 19 pounds of resistance, all you're doing is plugging in 19 for this r up here. So in doing that, you get 8/3 times 19 plus 40 over 3 is equal to L. So that's going to be your length. And this just makes it easier finding the inverse, just so you don't need to do extra steps in solving for your resistance. All you do is plug in your resistance right here, and then bam, you get an answer. So once you multiply all this out and then add that 40 over 3, you end up getting 64 is equal to L. And that's going to be the length of your band with the 19 pounds of resistance. So let's go ahead and move on to example number 6 now. We're talking about the same kind of thing, doing the inverse of a model. So again, with this inverse of a model, we don't actually interchange anything. So looking at this problem here, it gives us this equation, P is equal to 35 t to the 0.192. And with that, it's asking us to find the inverse model that gives time as a function of the average ticket price. So now we're having it in terms of P, all right? So we want time as a function of P now. So in order to do that, we need to get the T all by itself. So first off, we're going to divide both sides by 35. And then you get P over 35 is equal to T to the 0.192. And after that, you can take the square root, or not the square root, you can take the root of 0.192, or you can take the opposite of that, or reciprocal of that. So square it to the 0.192 on both sides, 1 over 0.192. And if you notice, 0.192 times 1 over 0.192 is just going to be 1. So this will leave you as t to the 1 is equal to p over 35 to the 1 over 0.192 power. After you do that, go ahead and put in your calculator, and 1 over 0.192 will give you 5.2. So you actually have p over 35 to the 5.2 is going to be equal to your t. Okay, so now you put everything in terms of the price. Let's go ahead and move on to example number 7. And example number 7 is a build off of this example number 6. And it wants you to use this inverse power that we just found out to predict the year when the average ticket price will reach $58. So now, instead of having to solve for P from your original equation, you can use this inverse and just go ahead and plug in 58 for P, raise it to the 5.2 power, and that will give you your time. And in solving that out, you're going to get 14 is equal to T. So it's 14 years basically after the 1995, which we're taking that from example number 6. So that will put us all the way in 2009. And 2009 will be your answer because it's asking for the year. So not 14. We're using 2009 as our answer. Okay, and that will conclude us at section 3.4.